All right, so a sampling distribution. It's a distribution of samples, every sample size possible. So if you think about it, right? Somebody got their phone handy? Somebody Googled the number of people in Wisconsin.
$5.779 million.
Okay, so let's suppose that there's like 5.8 million people. So if we created a sampling distribution of size 50 for Wisconsin, which has 5.779 million people. The idea is that we would create every possible 50-person sample you can create out of these 5.779 million people. That would be an enormous number of samples, okay? I mean huge, right? Technically, this would be a combination of 5.779 million people taken 50 at a time. This is not something that a calculator could compute. This is not something that a computer would compute because the number is too large. This is a huge number. It's just an uncountable number. But the whole point is that mathematicians now can use this to actually start proving things about what's going on. All right? So, the central limit theorem gives us the ability to say that the mean of all of those 50-person groups written as mu with a little sub x on it, where x represents the 50 size group that we're creating, will always equal the mean of the total population. Always.
When you say you're going to make 50-person groups, what do you mean by that? Are you doing it by what?
So grab 50 random people from Wisconsin. Grab another 50 random people from Wisconsin. And as long as it's not the exact same group, do it again, 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 again,
So they're doing
Yeah.
like,
forever. Until you've gotten every possible group of 50 different people in Wisconsin that you can get. Every single one.
for what purpose?
To sample something, to ask them, say, what's their average salary? Or to ask them, what's their, blood pressure? Or to ask them, what's their weight? Or to ask them any statistical piece of information that you want to know about the state of Wisconsin.
But technically, our population has small children in it and such.
Yeah.
So some small children cannot tell you
Yeah.
certain things. So why would you want the full pop?
Well, I mean, we could break it down to just say 18 and older Wisconsinites. That's fine if it makes you feel better.
Well, it just doesn't make sense if you use the whole population equals little small children.
Well, yeah, but if you wanted to figure out, say, what was their average blood pressure, you would want to average in little people as well, right? I mean, so, or you may want to average in sort of how tall they are at a given time, right? Because, just because,
Some people have higher blood pressure than at a certain age, in their age group,
I
so a
agree.
certain level, so
Of
it's
course.
not matching correctly.
I agree, but all I want is the overall average of the entire state, that's all I care about.
Okay.
I mean, again, you can, for whatever purpose you're looking for, you can subdivide and narrow your sampling. But I'm just saying, if I'm just trying to do something for the entire state of Wisconsin, and it could be, how many children do you have, right? Kids don't have kids yet, but they still are a person in Wisconsin, and they would have none, right? So again, there you go, sort of these sorts of ideas.
So would this be like a big population or small population, or could it be both?
People, right? Again, I mean, I could be creating, 5,000 person groups if I wanted to. Again, it doesn't matter what the size is, just as long as you find every single one of them you can in the population, that creates what we call a sampling distribution. So that's the key, is just defining this sampling distribution, which is a sample of samples, which again is another one of those sorts of things you have to wrap your brain around, right? This isn't just asking 50 people, it's asking 50 people and 50 more people and then 50 more people and then 50 more people, as many different 50 groups of people you can. Yeah, And then you're trying to imagine what's true about all of those 50-person samples. So don't think about any one individual group of 50 samples, think about the entire group's data as a set of data. Again, this is the sort of thing mathematicians love to do, is they look at totals of totals, averages of averages, sums of sums, right? This is where we're getting to, all right? And the big kicker to it, right, is that these things are true. That if you average out, if you take the average in every group, and then across every 50-person group, you average all of those averages, you will always get back to the average of the total population, all right? So in other words, the mean of the sampling distribution is the mean of the population. That is a truism, all right? And that's what the proof of the central limit theorem shows, is that there is no way that you can take all of those samples of 50 people and not have the average of them average out to the actual average of the population. It has to work, all right?
So the mean of the sample distribution is the mean of population.
Bingo. Which is nice. So if I tell you what the mean of a sampling distribution is, you can by definition tell me, hey, I know what the mean of the population is. They're the same. Okay? Which is nice. And then the cool part about it is that if you look at that sampling distribution and you try and find its standard deviation, right? So this is the standard deviation of the sampling distribution. So if you take all of the averages of all of those 50-person groups and figure out what the standard deviation of all of those numbers are, it turns out that this will be exactly equal to the population standard deviation divided by the square root of n, where n is the size of the samples in your sampling distribution. And so again, what it does is it gives you a feel for the relationship between the big, huge group of samples that you've created and the actual population itself. And that there's this relationship between it and the number of people you're actually asking, right? All right. Now, again, I am not going to go into showing you why any of this is true, okay? There's there's a ton of math that goes behind this to sort of say this is why this is true, but it's not something that I want you to worry about or that I want you to necessarily have to reproduce, okay? So what I want you to be able to do is to understand, one, what a sampling distribution is, right? Taking every sample of a certain size that you can in a population, right? And the population can be big, the population can be small. It doesn't really matter. It's just realizing that that is something you can do. And that when you do it, it provides you with tools, all right, that you can use to start talking about the population, all right? And again, what we're going to do is to take this knowledge and utilize what we were doing in the last chapter a little bit to start actually talking about how we can start predicting things in the population based off of things we find from a sample, all right? What we've sort of been doing up until now has been saying, well, if we know the population already, i.e. we know the mean is 150 or 220 and the standard deviation is 40 or 50, we know how to figure out what percentage of people are going to have certain conditions, right? And this is based on us knowing the population first. But very rarely do we know everything about the population. So what we need to do is to go backwards. We need to say, hey, I took a sample of 50 people. What does that tell us about the overall population? That's what we need to be able to do, and that's what statistics allows us to do. In order to be able to do it, we have to know these things first, because we're going to use them, all right? Again, in a graduate level statistics class, folks, you would get the proof of this, and you would be bored so silly that your brain would sift out of your brain on the right-hand side and have enough time to go back in on the left-hand side and reformulate before the lecture is done. The math is immense, okay? Powerful and immense, but just daunting as all hell. So, I'm just going to stop right here and let you guys have this for free without showing you why, okay? So, yeah, there's some homework questions, but the homework questions are something along the lines of, if a sampling distribution's mean is 25, what's the mean of the population? Well, no, just mean. Yeah. If I tell you that the sampling distribution's mean is 25, you guys can tell me the population mean is 25. And you're done. I mean, that's all it takes, right? I mean, those sorts of relationships are what you can now use to your advantage, all right? And the homework is basically just asking you to use those two formulas and apply them, okay? And that's all I want to say about 6.1, all right? Or 7.1, yeah. All right, so, okay. Okay. So we have this set of formulas. That states all right, so how do we use this to start working with things? Now, one of the things that we need in order to make a lot of this work, folks, is we need normal distributions, all right? So part of what we're going to assume for a while here, at least in Chapter 7, is that everything that we're working with here is a normal distribution, all right? All right, so So if our normal distribution has a mean, and again, I'm just going to make up some numbers that we can play around with that are going to make it relatively easy to work with. A mean of 10. And I'm not, again, this is just so that we can play around with the actual data and figure out what we're trying to do with the information we have in there. And a standard deviation of 2. All right, so what is the probability that I sample, let's say 50 people, and the mean is, whatever, say less than 9.5. So, normally, when we were just sampling one person, we only looked at one person, we would do this the same way we were doing back in chapter 6. We would probably say, what's the probability that x is less than 9.5? And we would convert our x's into z's and go about our standard z calculation formulas, right? We would say, this translates into the probability that z is less than 9.5 minus 10 all over 2, and we could do all of that, all right? But that's only if we were asking one person. But because of that central limit theorem and what we had just a second ago, we now have a slightly new twist to it. We now understand a little bit more about what happens when we have a sample of 50 people, all right? The cool part is that the way we translate it into z is exactly the same way as it was before. We just need to use the fact that we're sampling 50 people instead of just one, all right? So, it starts the same way. Alright? We're going to convert this into a z. And the means are going to stay the same because the mean of a sample and the mean of the population are assumed to be essentially the same. So we get to subtract 10. But here's where it changes, right? Instead of using the standard deviation, we now have to use the sample with the standard deviation. And there's the twist. So the big twist in chapter 7, and what the central limit theorem basically allows us to be able to do, is to say, hey, all of this likelihood stuff, all of this probability that we were calculating before with one person, we can now translate to n people, where n is however many people we want to ask in our sample. And this starts to give us power, okay? Because now we can start really trying to figure out what the samples can give us, all right? So, let's crank through this. So, what's 9.5 minus 10? Negative 0.5. Now, please be careful. Is that what it worked out to be? Be a little bit bigger than that, maybe not. No. Oh yeah, 0.7677. Again, since it's a z-score, round it to the nearest hundredths. So what is the probability that z is less than negative 1.77? Now you can go back to your table. Has everybody gotten this number to work out on their calculators?
No, I put it in like a fraction.
Yes, exactly. You can do negative 0.5 divided by it, and parentheses 2 divided by square root of 50, that works as well. Just got to be careful with that. What was that? So this is the sort of truism that we are learning, folks, is that if you are pulling 50 random numbers from a set of data that is normally distributed about 10, the likelihood that the average of those 50 numbers being less than 9.5, and note, 9.5 is not very far from 10, right? But what's the likelihood of that happening? Almost, almost negligible, right? A 4% chance tops. This is what's starting to show us why this is so powerful and why we can start making predictions once we start asking enough people, right? So if we start, as long as we're not purposefully being biased, again, built into all of this, folks, is that we are not purposefully asking a certain set of the population a specific question, right? So if we were asking for average salary in the state of Wisconsin for a person over 18 years of age, we would not walk into, say, downtown Milwaukee and only ask people that were living on the street, because then the average would be very low. Whereas at the same time, we wouldn't also walk over into, Waukesha or Wauwatosa or one of the really nice fancy neighborhoods and ask all of them what their average salary or what their salaries are, because then we would have an average that was on the other end of the spectrum, right? So as long as you are truly being random, and this is what people potentially complain about when it comes to statistics, is how do you prove that the people who you sample were truly random? And that gets us back to chapter 1 about biasing and how do you choose a correct way to find your random set of people. But if you are truly doing it randomly, these are the sorts of things that are true about it. All right? So, let's go into 7.2. And which ones did I ask in 7.2?
2, 8, 12, 16, 20, and 26.
2, 8, 12, 16, 20, and 26.
Yeah.
All right, so how about we do one of the odd exercises in 7.2? Because, wait, did I ask 8 or 10?
You did ask 10.
Okay. So I'm going to do number 9 for those of you that have the book. 7.2, yeah, so page 311. All right. So if they say the mean is 100 and the standard deviation is 15 for some normal population, okay? And their first question is, what is the probability that I choose one person with a score less than 95? Exactly. This is the chapter 6 way, because how many people do we sample? One person. This is basically doing chapter 6. All right? So this says, what is the probability that x is less than 95? And we translate x into z the same way we did back in chapter 6, because we only asked one person. So we say, this is the probability that z is less than 95 minus 100 all over 15. (95 minus 100 is -5. -5 over 15 is 0.33333333. Go to your tables, look up -0.33. All these annoying tables that go the other way.
3707.
3707, is that what it is? And again, if you want to, you can say 37.07% is the probability. Whatever, either number is perfectly fine. And this is just a repeat of chapter 6. So, hopefully now the next question asks us the chapter 7 question. All right, so here we go. If a random sample of 50 people are asked, all right? So, random sample of 50 people, i.e. n equals 50. What is the probability that their average intelligence is less than 95? Find the probability that x is less than 95 this time. And now we use the new formulas that we were playing with. We still go to z. 95 minus 100, but this time it's all divided by 15 over the square root of 50. So take 0.333333 and multiply by the square root of 50. Should be like 2.1 or something like that, 2.2 something.
2.36. But negative.
Negative 2.36.
Yeah.
Sorry. Probably that z is less than negative 2.36. And what's the probability of this happening? A less than 1% chance that you sample 50 people and the mean is more than 5 units away from the actual population mean. These are the sorts of things that make this stuff good to see, right? Because this is what it means to utilize statistics properly. You should not be able to sample a large number of people and have the mean of that sample be a long distance from your actual real mean. It should be relatively close. And this is sort of proving that fact to you.
Oh, right, no worries, because the square root of 1 is 1.
Yes, And that's why when n is 1, it's just exactly what it was before. So it's really the same formula in chapter 6, it's just that since n was 1, we didn't write down the square root of 1 underneath it, so it doesn't matter. All right, so now, don't forget your truisms of probability, folks. Still sampling 50. What's the probability that x is greater than 95? You don't need to do any calculation for this. Well, I mean, a little bit, but
99.09.
don't forget the basic rules of probability, folks, okay? If you know what the probability of something less than something is, the probability of something greater than it has to be whatever its complement is, okay? They always have to add up to 1. That's just a truism, all right? So please don't forget that. You could go through the calculations and you would find out it's the exact same number, but yeah, you're just wasting time because you know what's true about this, all right?
I think I did that earlier.
It's not uncommon to do it once, and hopefully once you see yourself doing it, you're like, oh, damn it, the head slap, and then don't do it again. Watch. All right, so let's see, what's D? The random sample is 50. What is the probability that the mean intelligence will be more than 105? So n is 50, and this time I want to figure out that.
And then get 0091,
Why is it 0.0091 then?
because we're off by 5 again, but in the other direction.
Uh-huh. Before we were going less than 95, now we're going more than 95. We said that the mean was 100, right? Back at the very top. So we can play around with it for a little bit if we want, right? You may even go through some calculations with that if it makes you feel good. But once you run through the numbers, you'll be like, hey, wait a second, that looks really familiar. This is the probability that z is greater than 2.37. Which you will immediately, now that you guys are starting to get functionally savvy with this, you'll say, hey, this is the same as the probability that z is less than negative 2.37. And we've already done that one, 0.0091. And if you can see that it's the exact same thing, except it's just the opposite side of a symmetric graph, you should then see that it's going to be the same value. Ooh, okay. So now, part E. So this is the kind of question I wanted to get to, because this is a very common type of question to ask. So again, we're sampling 50 people randomly. Getting to define random correctly. What is the probability, the mean of my sample varies more than 5 units from the population mean? Okay, what does that mean?
Is that the MX&M part?
Hmm?
Is that the part of the MX&M part? Was your
No, nope, not quite. We did this? You're correct, we did this.
That's the 100 or 95 and 105?
Uh-huh. Except if it varies more than 5 units, what two numbers vary from 100 by 5 units? 105 and 95. And if they are more than 5 units, it has to be less than the negative 95 plus the probability that it's more than the 105. And
The in between? Or, well,
it's the two tails, right? There's the tail on the left and the tail on the right. And what do we know about these two tails, folks? Yes.
unit symmetry.
Yeah, they're the same, and not only are they the same, but we've already done both of them. What did we do in part B? X is less than 95. What did we do in part D? Greater than 105. 0.0091 plus 0.0091. What's 0.0091 plus 0.0091? So the probability of my mean being more than 5 units away from the population mean, either above or below, is just the sum of the above and the below, which again is one of those where when you see it, you're like, well, duh. Right? But again, it's one of those where you kind of have to go through the motions, beat the drum a little bit to see that, yeah, okay, it is kind of what you expect it to be. All right. So that kind of gets us through the first 2 sections of Chapter 7. Again, this is just the first step towards understanding how this stuff works in a sampling as opposed to just individual values, all right? We will carry it on Wednesday into 7.3 and 7.4 and finish up the first half of the class. I am here on Tuesdays and Thursdays from noon to 3 in my office. I'm also usually here in the mornings from like 8 to 10 if you're a morning person.
No, I don't get off work until 11. Unless you're here before 4 a.m., you know,
No, I'm usually waking up around then
I'll be already at work.
though. Ugh, sorry. I try hard not to come into work by 4 because the doors are locked and they won't let me in.
I was looking at the weather.
Yeah, is it snowing yet?
There was some sleet coming in for me.
There was hail.
Hail?
Yeah, pretty much.
Well, it was supposed to be between rain and snow all day today, or all night tonight, let's put it that way.
It's been changing by the hour, literally.
Right. Yeah, depending on whether the temp goes up or down far enough.
Yeah, because also wind direction.
I suppose.
Because we were supposed to get snow in
Taking
Evansville like noon, and then all that shifted about northwest, so it started going away, and
Oh.
then it started breaking up. And
Nice.
then it came back, and then it
And
moved
now we're having it again, and
when I looked at it this morning, I'm like, wow.
Don't forget your soccer thing. I'll probably be in tomorrow.